All right, so the plan for today is to finish chapter 2. We are going to learn the Bayes rule, the law of total probability, and we'll be able to solve some interesting questions. Some of the outcomes of these problems are really practical. They address practical problems that we face everyday life, like the accuracy of diagnostic tests in health sciences and things like that. All right, so I'm going to quickly recap what we have talked about last week. And in this 50-minute lecture, I will try to finish the remaining part of this chapter. And also on Thursday, after our Thursday lecture, actually, I'm also going to give you a reminder on Thursday. We are going to have on Thursday, we are going to have our first quiz at 6 p.m. It's going to be available on AutoClass, and you will have one day to work on the. It takes about 5 to 10 minutes actually. I already solved it, but you'll have one day to work on it, and it's going to be about these topics that we are going to learn today: conditional probability, Bayes rule, law of total probability, and things like that. All right. So remember we talked about in terms of probability when we defined the axioms of probability. We have first identified that the probability of the empty set in the sample space, the empty event, has a probability of 0. And the probability of the sample space, the entire set of the sample space, has a probability of 1. And any two events which are mutually exclusive, their probabilities can be added directly. All right, so here we use the set analogy, the set theoretic explanation of these probabilities. And if there are two events like this which are mutually exclusive, okay, mutually exclusive events means that they do not have an intersection. Their intersection of the when you look at the outcomes in these events, an event is a subset of the sample space, so it's a set of outcomes. So if you look at the intersection of these two events, A and B, they don't share any outcome together in these subsets. It means that their intersection is empty. We call these events mutually exclusive events. All right, and if we have these mutually exclusive events, we can actually define an event saying that what is the probability of A or B happens. We can find this probability by simply adding the events of these, adding the probabilities of these events, okay, for mutually exclusive events. If they're not mutually exclusive, we have also seen what we can do. If they're not mutually exclusive, if they share some intersection, okay, A and B like this, what we need to do is, if you want to figure out the probability of what is the probability of A or B, this event, we add them. We add individual probabilities, and also we need to subtract the intersection part, because during this addition, this intersection is counted twice, and this is this has to be subtracted. Also, we have talked about if two events are given to you as independent events, we are going to talk about the conditional independence and conditional probability later, but it's the same thing. If two events are given as independent, we can find the occurrence of both of these events. Event A and event B is observed. The probability of their intersection, or the probability that both events occur, can be obtained by simply multiplying their individual probabilities, given that A and B are independent events. Sometimes this is given in the question, sometimes not, but we may be asked to find out whether they are independent or not we may be given additional information about conditional probabilities, and that may help us to figure out whether they're independent or not. But this was another thing we have learned. For independent events, if A and B are independent events, the intersection is simply the multiplication of their individual probabilities. And we may have a number of independent events, and if all of them are independent of each other, we can multiply those probabilities with each other like this to figure out, to find out their intersection. Okay, there may be a D here. You just, if they're, sorry, this is going to be D. If they're given as independent events, they can be multiplied. And there were some examples about the reliability problems. I'm going to skip that part. I mean, we already went over that last week. I'm not going to recap that part. Now I'm going to directly talk about the conditional probability, which I made some small introduction and to when we were describing mutual exclusion and describing that mutual exclusion is not the same as independence. And while describing these terminologies, I defined something as conditional probability. If you remember that conditional probability is the probability of an event given that some other event has already been observed. So for example, again, if we have two events like this, A and B, okay, this is their intersection. And as I said, these are not mutually exclusive events because there is something in their intersection. So the conditional probability is defined as, for example, is given by this pipe symbol. So it means that given that the event B has occurred, what is the probability of A? And that probability basically is defined. If B has occurred, if we know that B has occurred, we know that our sample space is reduced now to this red region. Okay, now our sample space is this one. Okay, if we know that B has occurred. This is what this information is telling us. And then what is the probability of A? We see that the probability of A, the probability of observing A at this sample space now is reduced to this region, which are the outcomes that belong to the event A as well. So in other words, we defined this as this, which is P A intersection B divided by PB. So it's this ratio. We know this becomes our new sample space. So the probability will be whatever the intersection is, its ratio over the entire probability of B event is going to give us this. And it gives, this equation also leads to the well-known formula of intersection for not independent events. If the events are independent, we know that it's equal to PA times PB. But this, as you can see, these events, for independent events, it may be like this, but they may not be conditionally independent. This is conditional probability. This is not about conditional independence yet. All right, so the conditional probability is defined like this. And if you look at this, it will PA given B times PB gives us the intersection of any two events. So they don't necessarily be independent. So this is the case. When two events are independent, it means that the provided information, so the conditional independence means that PA given B does not change. This is what conditional independence is. If this additional information that event B has happened does not change your belief on event. Yeah, the PA is the event that PAB. PA intersection B is both event A and event B happens. PA given B, on the other hand, is the probability of observing event A given that. So this pipe here means event B is given. Given event B has occurred. Given means that we know that the whatever we have observed this time now, whatever outcome we observe, it's one of this. It's coming from this sample space. So given event B is like an information somebody's given to you that, okay, I'm not going to tell you which outcome it actually is, but I can tell you this: it's event B. Okay, it's when we are given that event B has occurred, it means that none of the outcomes that are outside here are observed. We are sure of that. So our samples, this is like this information reduces your entire sample space to the events, to the outcomes that are only contained within B. All right. So given that an outcome within the set of B has observed, and we don't know what that outcome is, okay? If we pinpoint an exact, if we see the observation actually, there will be nothing probabilistic about it at the end. But given, and I'm going to solve a question about this in a moment, and it will be much more clear about what we're talking about. But this is given event B, what is the probability of event A? If this doesn't change, if given event B, probability of A still is the same as the probability of A without this information, in that case, we call that event A is conditionally independent of event B. And this also means that event A and event B are independent, because the vice versa is also true. Because this formula that I had written here is a general formula which is true for conditionally independent or not independent events. Okay, so this is a general formula. This, as you can see, this is the definition of conditional probability. The conditional probability is defined as the ratio of, because the probability that A is going to occur is only in this area A intersection B, and its ratio over the entire event B is the definition of conditional probability. So the thing that you see here at the top, this formula, is the definition of conditional probability. It's not whether they're independent or not. Okay, for all the events, this holds. A given B is this formula. Now, here, but if two events are independent from each other, we know that for conditional independent from each other, also the same thing. Okay, these are the conditional independent, or they're independent. The independence is only one thing. So in other words, PA given B is equal to PA. I define this as conditional independence, right? Now, if you plug in PA here, because they're equal, right? PA given B is equal to PA. What do you get on the right-hand side of this formula? PA intersection PB is equal to PA times PB. Where did we see this? We see this just in the previous slide, saying that if two events are independent from each other, their intersection is their multiplication. So here is how independence and conditional independence, or they are the same thing actually. Two events are independent, their intersection is this. So if A given B is equal to A, just replace that with PA, what you get is their intersection is just their multiplication. Okay, now from here, we can actually also prove that. What is, if I ask you, what is PB given A? If A is independent of B, given the information B, if the probability of A given B is equal to PA, what is the probability of B given A? If some, can we say probability of A? Yeah, exactly. For if we are known that, so B difference A has occurred. So this is something interesting. So because these are A difference, this A complement and A are mutually exclusive events, right? So we can say actually for any mutually exclusive events, if there are two mutually exclusive events, let's say they are A and B. If A and B are mutually exclusive events, given B, what is the probability of A? It's always 0, okay? If there are two things are mutually exclusive, if you know the first one has occurred, of course, it means that the other cannot occur. Oh, let me see. Yeah, I think I'm recording. Yeah, thank you for reminding. I could have forgotten that, but yeah, I'm recording the meeting. Thanks for the reminder. So these are all good questions. If two events are mutually exclusive, then the conditional probability that one of them is given what is the probability of the other, it's going to be 0. For mutually exclusive events, this will be 0. And when you say here P difference A means that the part of B that doesn't include A, these are the right hand side of the equation and the left hand side of this, the P difference, B difference A and A are two mutually exclusive events. Therefore, the conditional probability will be 0. Now, let me get back to this other question. What is the probability of, if two events are mutually exclusive? Also a very good question. If two events are mutually exclusive, can we say they're also independent? No, we can't say that because, okay, let's see. Maybe we can say. Let me try to answer this question. We have two mutually exclusive events. No, they're not independent because the independents say that A given B should be equal to PA, right? So for mutually exclusive events, this is not true. If A and B are mutually exclusive, PA given B is equal to 0, which is not equal to PA. Okay, so independence, mutually exclusive events are not independent. Actually, it shows that they're very dependent, right? Because if somebody tells you, imagine you have two mutually exclusive events. Okay, if somebody, like, you either have the disease or you don't have the disease. These are two mutually exclusive events. So if somebody tells you you don't have the disease, does it change your belief that you have the disease? Of course, it changes that the other's probability is 0. So they're not independent. Mutually exclusive events are very, very independent because they're very dependent. Very, very dependent because the knowledge that one has occurred reduces your belief in the other event to 0. Okay, that means they are dependent. Independence means that your belief in one of them doesn't change the belief in the other. So knowing that B has occurred doesn't change whether the probability of A is going to happen. Now, let me go back to this one. What is B given A? For example, A given B is equal to PA. Okay, A is conditionally independent given B. Can we also say the same thing for B? Or in other words, is this also true with just these information? Let's see whether that's not. I was going to ask question mark here. It's going to be, let's see. What is PB given A without the knowledge of all the, by using this conditional probability? Doesn't need, so just look at this case, all right? A, B, and their intersection. So what is PB given A? Let me write the definition of conditional probability. PB given A is equal to P B intersection A divided by PA, right? Okay, this is the formula that is conditional independence formula. Now, I just know from here that PB given A, if this is the case, if A given B is, if this is true, if this first part, if A is conditionally independent given of B, if given B, A is independent of B, like this, their intersection, we have seen that we can write in terms of intersection, we can write this due to this formula. Okay, we can just write their intersection is equal to PA times PB. Okay, then since PA intersection B is equal to PB intersection, that intersection is commutative. So what I can write here is PA times PB because of this. And PA's cancel each other. And what do we have here? If they're conditionally independent, PB given A is also equal to PB. All right. So if A is conditionally independent of B, B is also conditionally independent of A. So if PA is an empty set, it means that the intersection is also going to be empty. If we have something probability of 0, that's a good question again. When we have the empty event probability of 0, none of these will be. It's like we have in that case, their intersection, this part is always 0, PA given B. So when an event has a probability of 0, we can never talk about the case when that event has occurred, okay? Because this will be undefined. If PA is equal to 0, such a thing will not be defined, right? Yeah, it's because you can, what I mean is that it's not going to be, you will not be able to write something like this, because can you say A is given? Yeah, it's an empty event. When we have, if some event's probability is 0, that's the only, an event's probability will only be 0 when it contains no outcomes, okay? Because every outcome in the case of equally likely case, it will have some non-zero probability. Only the empty event has the 0 probability, and you can never write this conditional probability for an empty event, because you will not be able to say that that event has occurred, okay? Because it can never occur. So that's really the probability of these conditional independence and probabilities are only for events that are not empty events. Because otherwise their discussion will be meaningless. We will not be able to conditionally say that, given that A has occurred. This is a contradictory to the definition, because empty events cannot occur. I can draw some independent events, like, for example, look at this. Now, do you want me to assign some probabilities here? For example, let's say, okay, now for example, let this be A, let this be B, okay? Now, given that these events are two independent events. For example, what if the probability of A is 0.3, the probability of B is, for example, 0.5, okay? Probability of B. If these are independent, the probability of here is going to be, what I'm writing here are the probabilities, okay? 0.15. So the probability of the entire thing, on the other hand, here, so I cannot say, for example, if the probability of this part is 0.15, the probability of here is going to be 0.152, because these are ratios. We cannot just split ratios. These are not counts. When you're writing things like this, you have to be careful. Since when you use the set analogy, you may tend to use the parts that you write here as counts, but probabilities are not counts, they are ratios, okay? So when I say probability of A is 0.3 here, it means that the ratio of the number of outcomes that are here over the outcomes in the entire sample set is 0.3, okay? Now, but here I wrote the probability. So what will happen is that, for example, if you want to figure out the probability of, so if they are independent, this should be probability of A given B since they're independent, for example, probability of A given B should still be probability of A, okay, which is 0.3. So what it should be is, here, whatever the ratio of this, so probability of A intersection B, which is 0.15, divided by probability of B, which is 0.5, should give us probability of A. It indeed gives us probability of A, which is 0.3, right? So if they're independent, probability of A given B should be equal to, if they're independent, so it should be equal to PA. And I just check, sorry, this is A intersection B is already 0.15. I know that. So this is probability of A given B. Probability of A given B is equal to probability of A intersection B, which is, since they're independent, which is 0.15, divided by probability of B, which is 0.5, and it gives me 0.3, which is correct. I'm going to do some examples, and we'll see in the events that are not independent, and also we'll talk about the total law of probability. So now I'm going to move forward, and we have shown that two events, the conditional independence holds both cases, okay, in both ways. There is, if they're independent, if events are independent, we find their intersection by multiplying their probabilities. Some of the examples, let's quickly go over example 2.31 in the book, which is, so these are some a conditional probability events. So as I said, this is the definition of conditional probability. If there are two events, and this is in the definition, we are known that P has a non-zero probability, B has a non-zero probability, then we can talk about A given B, this probability. If B has a probability of 0, an event has a probability of 0, this will not be defined because given B, A given B will not be meaningful. And this is the exact same thing I wrote on the slides. For example, if you look at this example on the slide, tossing a fair die actually, because we are going to, I think, throw a single die. Dice is plural. So the number on the die is even, is the event. So we can actually draw these quickly. And the number on the die is less than 4. So let's write these events. So here's my sample space, which contains 1, 2, 3, 4, 5, and 6. I just threw them out. Sorry, let me actually, even numbers, let's put them together, 2, 4, and 6. And odd numbers, 1, 3, and 5 here. And one of the events is, the number on the die is even, that's event A. So this is event A. Event A is this subset. And the other is, the number on the die is less than 4, right? The number on the die is less than 4, it's 1, 2, 3. So the set here, in the other case, is 1, 2, 3. So this is the other event. So this is event B, and this is event A. As you can see, they're not mutually exclusive. Now, here is what we are asked. What is the probability of A given B, right? This was what what is the probability of A given B? Let's see, probability of A given B is equal to, if these are all outcomes are equally likely, meaning that I associate the probability of 1 over 6 to each one of these 6 outcomes, probability of A given B will be equal to probability of A intersection B divided by probability of B. And probability of A intersection B, since there's only one outcome in their intersection, it's 1 over 6. So probability of A intersection B is 1 over 6. What is the probability of B? There are 3 outcomes in probability in this event B, each one of them equally likely. 1 over 6, 1 over 6, 1 over 6. It's 3 over 6. Okay, so 1 over 6 divided by 3 over 6 is going to give us 1 over 3, right? Yeah, 6 is canceled. So the probability of A given B is 1 over 3. Now, what was the probability of A before this? Probability of probability of A, the unconditional probability, given, if you're not given what the event B has occurred, probability of A was equal to 1 over 2, right? Because it contains 3 outcomes. Now, the knowledge that probability the event B has occurred reduced our probability of A from 1 over 2 to 1 over 3, which means that A and B are not independent events. Okay, these events are not independent. The belief that B has occurred changed the probability of event A to 1 over 3. So this is one example. There is the example 2.13. So yeah, here you have proved that these things, if PA given B is equal to PA, if this conditional probability is the same as the unconditional probability, which we call that event A is independent of event B. And if these two events are independent, then by using the conditional independence formula, we can write the intersection like this. They all check out. We also showed that the vice versa is also true if they're independent. PB given A is also equal to PB. And this is the thing we also discussed. If they are disjoint, by the way, the term disjoint also means mutual exclusion. Okay, mutually exclusive sometimes is labeled as disjoint events. If they are mutually independence does not mean mutual exclusion. If they were mutually exclusive, PB given A would be 0. We also discussed this. Now, again, some exercises which are really simple. PA given B, B given A, what is PA, what is PB? Again, these are about tossing a single die. Okay, you can try out this example on your own. I'm going to now go over a little bit more complicated example with some probabilities. Example 2.31, which is about flight arrival and departure. Okay, I'm going to just spend like a couple of minutes on this one. Let's see, 2.31. All right, so I will just block the answer to this. So here, 90% of flights depart on time. 80% of flights arrive on time. So we have two events here, okay? Departing on time and arriving on time. Let's label these events as departing on time is this event and arriving on time is this event, D and A, okay? The knowledge that is given to us in this example, 90% of flights depart on time, basically tells us that the probability of D is equal to 0.9. Similarly, probability of not D is equal to 0.1, which means that 10% of the flights do not depart on time. These are exhaustive. An event's complement is mutually exclusive of that event, and it's an exhaustive, which means that its complement is 1 minus whatever that probability of this. And let's look at the arrivals. 80% of flights arrive on time. So the probability of this arriving on time is 0.8. By the way, this is D and A. I just named them like this. Whatever the question semantically labels those events departing on time, I just labeled as D. You could have labeled this as DO or AO to indicate their arrival departing on time. So, but I just use a single letter. And this is also what the book uses to describe those events. In other words, probability of not arriving on time is also 0.2, the complement. Now, here is what we are asked. You are meeting a flight that departed on time. What is the probability that it will arrive on time? Interesting. And also, they're also given something else. I forgot the last bit of information. 75% of flights depart on time and arrive on time. So what is this information? It's both events happening at the same time. It describes an intersection event, okay? Depart on time and arrive on time. And it's 75. So we are not given information about whether they're independent or not in this question. If they would be independent, we would just say that if they're independent, we will just multiply these two numbers and say, oh, it's 0.72. It should be 0.72 if they're independent. And if we are given that this A intersection D event, arrive on time and depart on time, is 0.75, it tells us that actually they're not independent because it's not equal to the multiplication of these. 0.75 is different from 0.72. Now, you're meeting at a flight that given that the flight has departed on time, what is the probability that it will arrive on time? So we are asked this probability. What is the probability of A given D? We just use our definition of conditional probability. It should be probability of A given D, A and D, intersection D, divided by probability of D, right? This is the definition. If we are given that it's departed on time, our sample space reduces to all the flights that departed on time, because not departing on time is not a question anymore. Now, It's simply 0.75 divided by 0.9, which is, let me use my calculator. Actually, it's also in the book, but let me just verify it. 0.75 divided by 0.9, 0.83. 0.83 is the probability of arriving on time, which is different, as you can see, from unconditional probability of arriving on time. So it's like our belief that it departed on time increased our belief on arriving on time, okay, which makes sense in this case. These are not independent from each other. These are events whether you have departed on time affects your arrival belief, whether it's going to arrive on time. But it's really interesting. It just increased the probability by 3 points, out of 3% points, from 0.8 to 0.83, knowing that it departed on time change your belief, but not that much, right? Because why did not increase our belief not much? Because the probability of arrival and departure on time is only 0.75%. If a larger number, this information will increase our belief even more. Now we can say that these two events are not independent. I will leave the question B and question, actually we already answered question C. They are not independent events, but I will leave part B to you as an exercise. Now I'm going to discuss something very nice, the Bayes rule. The Bayes rule is this. Sometimes we are asked, by the way, because of this symmetry, we know that PA given B is equal to PA intersection B divided by PB, right? So this is one formula for conditional independence. And the conditional independence formula for PB given A will be equal to PA intersection B, again, or B intersection A, it doesn't matter. So the numerator is the same in both of these terms, divided by PA. Okay? Now, if you look at these two equations, there is one common thing here in both of them, PA intersection B. So so it means that PA given B times PA for any events, okay? This is true for any events. They don't need to be independent or other. These are the general formula for conditional independence. So for any two events, any two non-zero events, because since we want to use the conditional probability given both of them, both sides, they should be both events which are with non-zero probability, and which will be equal to PB given A times PA, right? So this is what we have, because both sides here are equal to PA intersection PB. This is also equal to PA intersection PB. Now, if you're asked the probability PA given B, it's also possible to compute that without the intersection, because in some questions you will not know the intersection. It's when you have multiple factors, actually, it's very difficult to collect this type of data. Yeah, you're right. Thank you. This should be PB. Sorry, this should be PA. This should be PB. Here is the wrong thing here. You're right. So I wrote correctly here. So it's PA intersection B is equal to PA given B times PB. Okay, so it was a typo. So this one is PB. Exactly. Thank you for the correction. And the one on the right-hand side is PB given A times PA. So both of them are refer to their intersection. So in data science, for example, sometimes it's really difficult to collect data of these intersection points, because as you have more features, these events may be like different features that you collect, statistics that you collect. And collecting these statistics together, finding the intersection of these probabilities in high dimensional features is really difficult thing to do. So we cannot usually obtain this data. This is not available in our data set. So computing the conditional probability in the absence of P A intersection B, which, so what it will do is PB given A times PA divided by PB. Okay, so I just put this PB underneath here, and this is the Bayes rule. Okay, so this is known as Bayes rule. Okay, so this Bayes rule gives me a way to compute the conditional probability of something given certain thing occur by using the conditional probability of some other thing. The vice versa. If you have the conditional probability of the other way around, and if you know the unconditional probabilities of these, and sometimes this unconditional, I will just tell you one more formula to compute this unconditional probability, again by using these conditional probabilities, because sometimes it may be easier to collect statistics about this event unconditionally, but this may be very difficult to obtain too. But we will be able to compute this as well. But this is known as the Bayes rule, computing conditional probabilities by knowing the conditional probability of the other way around. And an example will clarify this. The very classical example, whether there's a diagnostic test to figure out whether you have certain disease or not. These diagnostic tests have different accuracies on when they are tested on a person with disease and without the disease. Okay, in other words, their specificity and sensitivity may be different. For example, they may be really highly accurate to identify a negative case. If you don't have the disease, they may tell this accurately 99% of the time. But if you have the disease, it will tell, for example, maybe only 95% of the time it will tell you have the disease if you really actually have the disease. And can we say that, for example, and we will be asked questions like, if the diagnostic result, because we don't know whether we have the disease or not when we get a diagnostic test. So given that the diagnostic turned out to be positive, what is the probability that you have the disease is something that we want to know at the end. Because does it mean that I have this disease 95% probability? No, actually, it depends on how rare the disease is too. All right, how rare the disease, because if the test came out positive, it also depends on it makes certain things wrong on certain parts of the population with the disease and without the disease. So this all of these information has to be taken into account, and by applying the Bayes rule, we will be able to figure out what is the actual probability that we have the disease. And sometimes this may be really counterintuitive to figure out that, okay, the test is accurate 95% of the time, and I tested positive. Do I have the disease with 95% probability? We tend to think like that, but it's not like that. The Bayes rule tells us that we need to take into account these other probabilities to compute this. Okay, so we usually, in that case, for example, we have the probability like, if you have the disease, the probability of the diagnostic to be positive is its accuracy. Okay, we know that. But we also need to take into account that what is the probability to test positive for any random people in the world. Again, this is not a probability that we may compute directly, but we may compute this probability, meaning that how rare is this disease? What is the probability that you have the disease without having any test, without the knowledge of performing any test or anything, any diagnostic? What is the percentage of the population that have the disease unconditionally? So these are those probabilities, and you'll see how we compute that. Now, in the last 5 minutes, I'm going to apply that. But yeah, I just want to also mention, in order to compute this part, we need one other knowledge, the total level of probability, which is this. Let me talk about now in a couple of minutes how to compute. Imagine we have an event A, all right? Now, if we have difficulties of obtaining, in the question, PA is not given to us directly, and we want to compute what is the probability of this event A. One thing we can do is, if we have a set of events which are mutually exclusive, let's call them B1, B2, B3. Look at these three events. They are mutually exclusive. They have a zero intersection, and they are also exhaustive. They span the entire sample space, which means that they do not leave out any part of A. Now, in order to find A, the probability of A, actually, we can write it as simply probability of B1 intersection A plus probability of B2 intersection A plus the probability of B3 intersection A, right? This is true, right? Look at this part. Look at this part and look at this part. These parts are mutually exclusive because B1, B2, B3 are mutually exclusive. So this will imply that B1 intersection with A will be mutually exclusive with B1, B2 intersection A as well. And since B1, B2, B3 are all exhaustive events, they cover the entire search space, sample space, the sum of these probabilities will cover the entire area of A. There may be, if you have another event B4, you may also call it like this in order to, if the intersection of B4 and BA is 0, okay, as you can see, B4A, doesn't matter. You still, to be on the safe side, you may add this probability, which is going to be 0 at the end, but you will get, by adding these intersection of mutually exclusive and exhaustive events with A, if you add those intersections up, you get the probability of A you're looking for. All right. Now, one common use of this is called the law of total probability. Law of total probability. And one common, very famous use case of the law of total probability is this. If you have some event B, its complement is this, right? B and B complement. What are these two events, B and B complement? They are mutually exclusive and they are exhaustive. So in other words, if you want to figure out the probability of unconditional probability of any event, and if you have the conditional probabilities of this event, if you have this PA, okay, let me first write the intersection. PA intersection B plus PA intersection B complement. This is true, right? B and B complement are mutually exclusive. They are exhaustive. So the probability of any event A is simply the addition of these two probabilities. I already told you that computing intersections is difficult, but we know that this intersection could be written as PA given B times PB. Okay, this is a parenthesis. And the right-hand side is PA given B complement plus B complement. So this tells you that to find the unconditional probability of some event, you can use the unconditional probabilities of these other events. If you know PB, it's 1 minus PB. Knowing PB means that you also know PB complement, it's 1 minus PB. And these may be the probabilities, the accuracies of the diagnostic test if you don't have the disease and if you have the disease. So testing positive if you don't have the disease, and testing positive if you have the disease. So these information will help you solve problems that are like this example. And I will just go over this quickly and you'll see. So this example, okay? So this example here, let's try to solve it by applying both the Bayes rule and the law of total probability, and I will try to do it as quickly as possible. So what does it say? There's a diagnostic kit which is 95% effective in detecting a certain disease when it's present. So this look at this sentence. It says that when a person has the disease, the diagnostic kit is going to be able to detect that. So it's going to be positive. So here are two things. Let's name these events. Testing positive, let's call it P, okay? Or no, we use P for the probability. Let's call it T, okay? T is the event to show that the diagnostic test is positive. And let's call D is the event to show that whether you have the disease. When you have the disease, when the outcome is have the disease, is this event D. All right. Now, the first sentence, if you look at what the first sentence tells us, if the disease is present, this disease kit, diagnostic kit, is going to be 95% effective, meaning that probability of T given D is 0.95. This is what it's saying. What about the probability of this? If you have the disease, what is the probability that the diagnostic test is going to fail? These are two complement events, right? So it's going to be 0.05. Okay. Now, this is the first bit of information. Look at the second case. The test also has a 1% false positive rate. What does false positive mean? False positive means that the test results is positive, but which is something false, which means that you don't actually have the disease. In other words, this sentence is saying that if for people who are known to not have disease, the test sometimes comes as positive 1% of the time. So it's this. The second is if you don't have the disease, the test sometimes comes positive. What is that probability? 0.01. In other words, if you don't have the disease, 99% of the time, the test will correctly say negative. Okay, so we are given these probabilities. Look at this. All the conditional probabilities are conditioned on, because when this diagnostic test is being produced, they are tested. They are tested on people people known to have the disease, and people known to have not to have the disease. So these are their tests. This is like this is its sensitivity. Okay, sometimes it's called recall sensitivity, and this is its specificity. False positive rates. False specificity is 0.99, or its false positive rate is 0.01. Now, here is the last bit of information we need. If we know that the rarity of this disease, if 0.5% of the population has the disease, okay, and this is the last bit of information we write is this: the unconditional probability to observe the disease in the population is 0.005, right? This is what it says. 0.5% of the population. So it's 0.5 in 100, it's 5 in 1,000. So 5 in 1,000, this disease is seen in 5 in 1,000 people. It means that the unconditional probability of not observing the disease, these are all complementary events, 0.995. Now, what is the question that we're asked here? What is the probability a person with a positive test result actually has the disease? Now, here is the thing. If your test result turns out to be positive, given that event T has occurred, what is the probability that you have the disease? This is the question we are asked. How are we going to compute this? Let me write it here. Probability of D given T, if we apply the Bayes rule, probability of T given D times D, and probability of T underneath, right? We are going to have the probability of probability of testing positive in the population. But this is not given in the question. We have PD, unconditional probability of PD. We have all these conditional probabilities, but PT is not given in the question. Here is the place where we apply total law of probability. In order to find PT, I will be using PT given D, the same thing that is above. That's really one of the things actually you should know is one of the summation terms here is going to be exactly equal to the term that is above. And the other is PT given not D times PD. P not D, like this. All right, look at this. D and D complement, they are mutually exclusive. PT is given below in the question. Let's see, what is PT? PT is not given, I think, here. The unconditional probability. I mean, if you just tested a random person in the population, what is the probability that the test is going to be positive? This is not given. This PT basically means that if you just select a random person from the population and test them without knowing they have the disease or not, what is the probability that the test result is going to be positive? We're not given this information. All the information that is given in the first two sentences is how the test diagnostic kit results in if we know that the person has the disease or if we know that the person does not have the disease. Okay, so all these PT and PT prime are given unconditional on the disease. Okay, so PT is, when you say below the question, we'll find it. So this is what that PT, we can compute PT. So this one, the probability that the population has the disease is the probability of PD, all right, the unconditional probability. Because without any test, the disease occurs in this much of the population, 5 in 1,000, we see the disease. Now, but look at the equation that I wrote here. All of them are the terms that are given in the question. PT given D, what is it? 0.95. What is PD? 0.005. So let me write that. 0.95 times 0.005. This is that one. I write the same thing beneath, 0.95 times 0.005. It's this part. And look at this other part. The probability of probability of the test positive in the case of not disease. It's this one. Right, 0.01. It's also given in the question. And probability of not having the disease, 0.995. Okay, so this is the probability we are looking for. And I will directly go ahead and look at the answer. So it's exactly the same thing we have written here, 0.01, 0.995. And if you compute this, the probability turned out to be 0.32. So it's a small probability, all right? But is it really a small probability? I mean, it's like, okay, less than 50%. You have less than 50% of chance you have the disease. So what did this test do? It increased our belief that a random person has the disease with 0.005 probability. This test has the power to increase that 0.005 to 0.32. A big increase, right? The test is not, you cannot say the test is useless. It's useful because without the test, we just believe that the person has the disease 5 in 1,000. Now it's 32 in 100. The likelihood that the person has the disease, I mean, you can consider if you define likelihood as the ratio of this probability over 0.005, let's also compute that. What I'm saying is this, 0.32 is after the test result positive, this is the probability that we have the disease. Without the test result, this was the probability we had. And if you look at this ratio of probabilities, the ratio of probabilities is no longer a probability. Because if you divide these two numbers to each other, it's going to be a number which is really large, which is 64. Okay, so it increased the likelihood that we have the disease 64-fold. It's quite higher than 0.045 exactly. So this is what the test did. Basically, it increased our belief in that the person has the disease. All right. But it's still much less expected than 0.95, right? I mean, the test is affected on if the person has the disease, the being testing positive is 0.95. I mean, the diagnostic test has 95% accuracy, but this does not mean that you have the disease with 95% probability when you test positive. This is what is really counterintuitive, and I mean, a layman that you visit on the street probably is not going to. They're going to any person. If you don't know the Bayes rule, you're going to think that if you test positive, you have 95% probability you have the disease, but that's not true. We are just shown that we have 32% of, 0.32 probability of having the disease. All right. So that's the Bayes rule and application of law of total probability. I'm going to solve another example on Thursday, but basically this concludes chapter 2. Sorry, I couldn't be, I took another 10 minutes of your time. Sorry about this. I will stop recording.